Okay, so today and maybe tomorrow we will discuss, will be sort of the concluding lectures on error correction, and also I would like to briefly introduce, whether in today or tomorrow's lecture, this idea of fault tolerance. And with that, we will wrap up this big module of this course. And we still have about 5 weeks of lectures, I think. So in about the next 10 lectures or so, we will talk about quantum Shannon theory. Okay. So we've discussed various aspects of stabilizer codes, and you've also even been tested on some aspects of that in your midsem exam. I hope all of you found the paper easy, and I hope you've done well. Although I don't see why everyone had to submit exactly at 5:30. The paper was only for 90 minutes. But I see that half the class decided that they have to hit submit at 5:30, and obviously Moodle gave up at that time. And then you're all getting error messages and you're all emailing various people. Anyway, yeah, but we did get all your exam papers, I think. Fine. So we've discussed this idea of an NKD stabilizer code, right? Where you take k qubits. So that's C2 tensor k dimensional space. That's a C2 tensor k space, right? That's the Hilbert space for this. They are encoded in n qubits. So this is a C2 tensor n space. And so you essentially find 2 to the k dimensional subspace of the 2 to the n dimensional space. And that constitutes your code. And the code can, such a code we showed that the D means this can correct. First of all, it can detect errors on up to D minus 1 qubits, and it can correct for errors on up to D minus 1 by 2 qubits, right? So note that here errors only means Pauli errors. And this whole concept of stabilizers and distance and all of that works only in this framework where all the errors are simply Pauli's. And this framework still helps us because any operator can be expanded as a linear combination of Pauli's. And so we use that to correct for arbitrary errors, right? So although I say errors equal to Pauli errors, the correct statement, so maybe I shouldn't say this here because it's kind of misleading. So let me say it can correct arbitrary errors, because any arbitrary error can be realized as AI plus BX plus CY plus DZ. Okay. All right. So there are a couple of aspects of stabilizer codes which I have not discussed. So let me do that first. And also, I would also like to give you some more examples of stabilizer codes. So the first aspect that I haven't discussed is the so-called logical operators. Okay, this is something you will find in the literature that is often discussed. So the idea is, you know that the stabilizer itself is a group, an abelian subgroup of this n-qubit Pauli group, and it is generated by there are some R operators where R is n minus k, right? So let me write this as n minus k. So these are the generators of the group, of this abelian subgroup, right? And now you associate with this a code space of dimension 2 to the k, right? So this is some vector subspace of the 2 to the n dimensional space. So the question is, what are the code words now? It turns out that there is an efficient way. So just like how we said, you can simply describe the code by the set of operators. And the code words, you have to pick them as some +1 eigenstate, common eigenstate of this set of commuting operators, right? That's how we constructed the code space, and that's how you would have done this for the 3-qubit phase flip code. That was a question in the midsem. We did the bit flip. We saw the stabilizers for the Shor code, etc. Right? But there is an efficient way to describe the code words rather than states. You can efficiently describe them again as operators. And these are the so-called logical operators. So now imagine I have this 2 to the k dimensional code space. So how many code words do I have? Yes? If it's a single qubit subspace, how many code words do I have? I have 2, right? I have the 0 logical and the 1 logical, right? Now, how many, instead of just 2, I'm going to have 2 to the k orthogonal states called logical states. Right? I have 2 to the k logical states, but only k logical qubits. Right? I hope you understand the distinction. It's like I have, so I have, let's say, one C2. So I have this, right? I have C2, tensor C2, etc. Tensor C2. So there are, this is k of them, right? So there are k qubits in all, right? So for example, your standard code space is just a single qubit. There's only one logical qubit, but there are two, obviously a pair of orthogonal states, the 0 and the 1. So this 2 to the k basically is because I have a pair associated with, okay, did I mess up? No, that's fine. Yeah, so I have essentially k log. Yeah, was there?
In when we code our state, right? When we write it in terms of basis of code space. So the single vector of code space, that basis vector, it contains n elements, right?
Yeah. Yeah, indeed.
Why am I confused? Because if the dimension of the code space is 2 to the power k, so that should be equal to the number of basis elements, right?
Yeah, indeed. That's all I'm saying. But I don't want to simply look at it as a 2 to the k dimension space. I want to look at it as a space of k logical qubits. That's the point. No, that's fine. See, if I look at my Shor code, then it has code words like this, right? So indeed, these are states of 9 qubits, right? This is a 9 qubit state, but how many code words do I have? I just have 2 of them, right? One is being the 0 logical and the other being the 1 logical, right? Is that clear?
We're taking a two-dimensional subspace.
Sorry?
Hello?
Yeah.
We have only two elements in the basis because we were taking 2 to the power 1 dimensional subspace.
Correct. Yeah, exactly. Yeah. But although I have two states, I'm saying that this constitutes a single logical qubit. So I'm just making the distinction between the number of logical qubits that you have and the number of these orthogonal states that you have to span the code space. Is that distinction clear? That's all. Okay. Right. So yeah, I'm just trying to make a distinction between how many logical qubits you have. And what I'm now going to tell you is that you don't need these full bases to describe this code space. Rather, it suffices to think about logical operations on the logical qubits. Okay, so what do I mean by that? So it's enough, for example, one way to describe these k logical qubits rather than writing down the complete code word itself is to ask, can I identify a Z1 bar, Z2 bar, etc., Zk bar, right? Which is a set of k logical Z operators, right? Which means these are operators that act like the regular Z operator. This is a single qubit Z operator on each logical qubit. Okay. And it will turn out that because so if I just think about the zero logical state, right? So the code space is now going to have several logical states, right? Not just two. There was a zero logical and one logical because it was single qubit. Now, if I think of encoding two qubits, there's going to be the 0 0 logical, the 0 1 logical, the 1 0 logical, and the 1 1 logical, and so on and so forth. You can keep adding them, right? So suppose I think of the all zero. So I'm going to put a 0 bar to say that now this is some k bit binary 0 logical, right? This is now going to be a +1 eigenstate of the Z1 bar, right? So this being the first logical qubit, So this being the first logical code word, this is going to be a +1 eigenstate of the Z1 bar operator, right? And similarly, for every logical qubit that I can find, not every logical state, but every logical qubit that I can find, I will associate a corresponding Z operator with it and call that the logical Z operator. So like I said, each logical state is now, so this 0 bar logical is not just the +1 for the Z1 bar, it should be the +1 eigenstate for all of these Zi bars. And then the next logic, so if you think about, for example, you're encoding 2 qubits, then this is what I mean. So there will be maybe like this, right? And now I have to find an effective pair of Z operators for this, which is going to then be a +1 eigenstate for, so there'll be 2 logical Z operators corresponding to each logical qubit. And then you can think of this state as being the +1 eigenstate of both of these, right? This state will be a +1 eigenstate of this and minus this. This one will be a +1 eigenstate of this and minus this. And this one will be a +1 eigenstate of minus of both these operators, okay? But the all zero logical, the all zero state I can identify as the common +1 eigenstate of all these k logical Z operators, right? So this is going to hold for all I going from 1 to k, right? And for each logical qubit, so if I now split this as 2 logical qubits, one way to think about this is to think of Z1 bar tensor Z2 bar as being the final logical Z in some sense, right? So I associate one logical Z operator with each qubit. Note that each of these in itself will be a 2-qubit operator in this case. And if I encode k qubits, each of them will itself be a k, well, each of them actually will live inside the n-qubit space. So they're all n-qubit Pauli operators. So sorry about that, saying that k. But these are all basically n-qubit Pauli operators, just like your error operators or your stabilizer operators. They're n-qubit Pauli operators that effectively act like Z operators on the logical states. Okay. So maybe let's write some examples and it'll become clear. But let me just complete this discussion of logical states by saying that you can also have logical X similar to logical Z. So you can also think about logical X operators. And these logical X operators are basically, so let me say that the logical Z are all operators in the n-qubit Pauli group. That's what I wrote down above as well. Now you can also think about logical X operators, which are basically such that xj bar, which have to behave like an X corresponding to each Z. What is the defining property of an X with respect to the Z? That it has to anti-commute. So one way of stating that is if I act this X operator by conjugation on the logical Z, the dagger is of course the same as itself, then I will have minus Z, right? So this is the defining property of a logical X vis-a-vis a logical Z operator. So the first thing to do is to identify a set of operators which behave like Z operators on the code words. But now it seems like a chicken egg problem because you tell me I don't know the code words. I thought you were going to help me find the code words, but instead you've given me a set of operators which you tell me that they act like Z operators on the code word. So how do you first get these operators? Well, one way to think about this is pick any set of K operators that commute with all the stabilizer generators. Because you realize that this zero logical state has to be, of course, an element of the code space. So it has to be stabilized by all the generators of the stabilizer. But now there is an additional set of K operators which also will stabilize it. So basically we have to pick K operators that commute with the stabilizer generators, right? So how to choose the logical operators? So yeah, this idea of logical Z might become clear when I discuss a few examples. So if you have questions, just wait until I do the examples and then things may become clear. So I just defined the logical Z here first. Now I'm just going to write down how do you pick the logical Z. So how to choose the logical Z. Once you choose the logical Z, you automatically, the X operators kind of choose themselves because of this property, right? So choosing Zj is to basically pick a set of K operators, which is Z1 bar, Z2 bar, etc., Zk bar belonging to Pn such that the Zi bar commutes with all generators. So this is for all I going from 1 to k and j going from 1 to r or n minus k. So there are n minus k stabilizer generators and there are k of these z logical operators. Okay. So this is how you pick the logical z operators, and once you pick the logical z, the x's pick themselves, and each of these logical z operators is an n-qubit Pauli, which effectively acts as a z operator for one of the logical qubits, right? But all of them will have to essentially leave the zero logical state invariant, because that's a kind of global property of the zero logical state, right? And then every other logical state will be a +1 eigenstate with a minus corresponding to that logical operator where there is a 1, right? Okay, so once again, the logical x is basically, so this also I mentioned that the xj bar is the logical x operator corresponding to the jth logical qubit, just like how the zj was the logical z operator corresponding to the jth logical qubit. Okay, so once again, let's go from the abstract to some examples. So we'll again revisit what we already know, and then I will write down 2 other stabilizer codes today, which we haven't discussed so far. So the 3-qubit, let's say the bit flip code, this was your 0 logical and this was your 1 logical. Now this is of course only a single qubit code. I won't write a distance here because it's specific to a particular noise. It's not a general purpose code. So I won't write a notion of distance here. So you know that the stabilizer group associated with this was essentially generated by Z1, Z2 and Z2, Z3, right? So now the question is, can you find a 3-qubit operator that commutes with both Z1, Z2 and Z2, Z3? So actually there are 2 such operators, right? So that is, you have Z1, Z2, Z3, right? And you have X1, X2, X3, right? And you will notice that in this case, this Z1, Z2, Z3 is indeed the logical Z operator, right? Of course, there are several more. You can say Z1 identity, etc. But none of them really qualify to be a logical Z operator for this one, right? And in this case, it's not, it's not a canonical example because, like I said, it's not a genuine stabilizer code. It's a specific code for a specific noise model, but it's useful to identify the logical it's useful to identify the logical X and the logical Z operator here, right? So why is this the logical Z operator? Remember, there's only one qubit that you're encoding. So there's only one logical Z and one logical X. Z bar acting on 0 logical gives me indeed 0 logical, right? And Z bar acting on 1 logical should indeed give me -1 logical, right? Why? Because it has 3 Z's and the 1 logical has 3 1s, right? So one of them, so I'll have 3 minus signs and one of them will remain, right? So this is what I meant by saying that if I now look in terms of code words and instead of logical qubits, if I say logical states, the all 0 state will be stabilized by all your logical Z operators. The next state here, which is the 111 state, is not going to be stabilized by the Z bar operator, but it will be stabilized by -Z bar. Okay. But Z bar in itself commutes with all the stabilizer generators. Similarly, the X bar, right, acting on 0L is going to give me 1L, and X bar acting on 1L gives me 0L. So it effectively acts like a logical X operator on the logical qubit. So is this idea of logical Z and logical X clear from this example? Any questions? Okay, so let's now try to identify the logical X and the logical Z for the Shor code. Okay. My Surface tablet is really acting up. This is another reason for me to just quickly move to in-person classes and write on the blackboard. Okay, so this was the 3-qubit code. Next we have, now you see things will get a bit more interesting. So let's do the 9-qubit code and try to identify, again, it's a single qubit code, but now I can write it formally as a 913 code, right? So we all know that this is a 913 code, and the 0 logical is basically this. And the 1 logical is this. And then we have identified the stabilizer generators. So as I write it down, I'm going to ask you, can you identify for me what is the 9-qubit operator which commutes with all the stabilizer generators and acts as a logical Z operator for these code words? You see, we are doing the other way around here, where we have the code words and we are identifying the logical operators associated with them. You can jolly well do the reverse as well, right? But yeah, right now we are doing this exercise where, right? So these are the Z stabilizers, and then you have the X stabilizers. Yeah, so what should be the logical Z operator? Again, there's only one logical Z and one logical X, right? Because there's only one logical qubit that is being encoded. So what is the logical Z?
Ma'am, all X operators, I mean, X1, X2, X3, X2, X9.
So Nilesh knows the answer already.
No, I just, sorry, I was not known, I was just thinking. Yeah.
So, yeah, good. That's correct indeed. So the surprising thing is that the logical Z operator in this case is going to be the all X operator, right? So this is going to be the all X operator. Why is that? So the function of the logical Z is to act on 0L and give 0L, is to leave 0L invariant, right? And if you think about the all Z operator, which is Z1, Z2, Z3, etc., Z9, and you act it on 0 logical, what do you get? What do you get if you act the all Z?
Zero logic.
I'm not hearing you properly. Anyone else?
Sorry, L1L.
1L. Ah, correct. Good. You see, so what is the all Z operator then?
X logical.
X logical, exactly. Good. So why does this happen? Because every set of 3, you see Z1, Z2, Z3 acting on 0 logical is going to take 0 logical to 0, 0, 0 minus 1, 1, 1 by root 2 on the first set of 3 qubits. Then you add the next set of 3 qubits. So then you add the Z on the next 3 qubits, right? And then you realize that you're doing you're going to have a relative minus sign on the second set of 3 qubits. And then you add the Z7, Z8, Z9, and then you see that you actually have a minus sign on the remaining last set of 3 qubits. And so effectively what you have is 0, 0, 0 minus 1, 1, 1 by root 2 tensor 3. And so that is indeed one logical, right? So the all Z operator, the Z1 to Z9, it does indeed commute with all the stabilizer generators, right? Because the stabilizers are pairwise Z, or I have an even number of X's, right? I have X1 to X6, or I have X4 to X9. So I have 6 X operators. So it commutes with all the, how many stabilizer generators do I have? 8, right? I have 8 stabilizer generators. So I have 6Z and 2X. So it commutes with all the 8 stabilizer generators, but it acts like the logical X operation on 0L, and of course whatever it does to 0L, I mean it's well, 0 and 1 come in there, right? It cannot act as the X on 0 and something else on 1, so it acts as the logical X operation on the logical qubit. So the X bar is indeed Z1, Z2, Z3, Z4, Z5, Z6, then 8, 9, and the Z bar is actually X1, X2, X3, because this is what preserves the relative minus sign, right? Because the X1, X2, X3 will act on the first 3 qubits and give you back 0, 0, 0 plus 1, 1, 1 by root 2. The X4, X5, X6 will again give you 0, 0, 0 plus 1, 1, 1 by root 2. It just flips the 0 and the 1 within each set of 3 qubits locally. So this indeed leaves the code state, it indeed leaves the 0L, all 0 state invariant. So it is a stabilizer for the all 0 state, and then the all, the one logical, I'm sorry, I shouldn't say the all 0, I should say the 0 logical. It is indeed a stabilizer for the 0 logical. And for the 1 logical, it will indeed pull out a minus sign, because again, it's going to flip the 0 and the 1. So within each set of 3, it pulls out a minus sign. So overall, it will pull out a minus sign. Okay. So I hope this idea is clear that these are now the logical operators of the Shor code. So you see, the point is, although the stabilizer itself fully identifies the code for you, it does not tell you what is that particular pair of states which you are using as the logical 0 and the logical 1. Once you add the X bar and the Z bar to the mix, this completes the picture. This completely defines for you the Shor code, which is a 913, right? Because it tells you exactly what is the subspace which is left invariant by this set of 8 stabilizer generators. When I say S9, it is that set of 8 generators. And within that, X bar and Z bar tell you exactly which pair of states you're picking as the logical states, as your logical 0 and the logical 1. It is that state for which, so the logical 0 is that state for which Z bar essentially is a stabilizer, right? And the logical 1 is that state for which minus Z bar is a stabilizer, okay? And in the case of the Shor code, you find that the roles of the individual X and Z are actually flipped. So what is X on a physical qubit, right? X1 is a local X operator on one of the qubits. This is what you will call a physical X operator, because physically, if I'm an experiment, I'm sitting with 9 qubits. But out of those 9 qubits, I'm making one effective qubit. And that one effective qubit, if I want to do a Z operation on that one effective qubit, I have to do this operation, which is this set of 9 X's. Okay. So is the idea of the physical X versus the physical, the logical X, the physical Z versus the logical Z. I hope that idea comes out clearly, right? So this is why, along with identifying the stabilizers of a code, you also need to always identify the logical operators associated with the code. Conveniently, so far, the codes that we discuss are all single qubit codes. So there is only one logical X and one logical Z. And the logical Z is often the easiest to identify because it is the one which is a stabilizer for the zero logical state. Okay? Any questions?
Ma'am, we need X bar and Z bar to identify which is logical 0 and which is logical 1. Is that it?
Yeah, indeed. Yeah. So this identifies a vector subspace for you. Okay, it identifies some subspace of the 9-qubit space. But in that subspace, what is my 0 and 1? Okay. Right? Yeah, that is what this additional information that these two operators provide. Okay, yeah. Okay, so that is one part of the story. The second part is what I was telling you last, which is that these two operators are also important to know once I'm in my code space and I start doing operations. So we'll come to this next. So between today and tomorrow's lectures, I want to complete the picture, right? So I have an error correcting code now, and I'm going to encode my qubits, and then I'm going to do quantum computing on them, right? My job doesn't stop with just doing error correction, right? So if I have some set of, how many lines have I drawn? Okay, so this is a set of 9 qubits, okay? So often you will find that this is represented with a single line with a slash like this. So this tells me that it's not a single qubit, but it's a group of some set of encoded qubits. Okay? But what are these encoded qubits useful for? Well, I would like to now do Shor's factoring algorithm using these encoded qubits. So I need to know how to do gates on these encoded qubits. And the first step towards that, again, is identifying these logical operations. In fact, not only do you have to identify logical X and Z, as you will see progressively in today and tomorrow's lectures, you have to identify logical gates on these operators. So the simplest thing that I need to be able to do is a Z gate or an X gate. So what I will do is the logical Z gate. Right? If I take a bunch of 9 encoded qubits and they are in some state alpha 0L plus beta 1L, I need to be able to do a logical Z operation, which will take me to alpha 0L minus beta 1L. Similarly, the logical X operation, X bar, right, is going to do the other thing. It's going to take me to alpha 1L plus beta 0L. So I need to start identifying what are the logical gates. So identifying the logical operators performs this other function also, where it tells me that it identifies for me 2 of the logical gates in a gate set that I need actually for universal quantum computing. So the logical gates X bar and Z bar are now identified once I identify the logical X and Z corresponding to that set of stabilizers. Right? And both the logical X and Z are indeed operators that will commute with the stabilizer, but they are not in the stabilizer, right? And so effectively, they are actually operators which are sitting in the normalizer of that stabilizer code, right? These are the operators which we said were error operators, and indeed they are, right? If I think about this, this 9-qubit X operator, this is not an, if it comes as an error, this is not something that my code will correct for, okay? In fact, such errors can occur, and these are called logical errors, and these are the worst kind of errors to happen. Because if a logical error happens, it will actually confuse my set of logical states, right? Because what does this thing do? It's actually going to take 1 to -1 and so on. So it will, for example, muddle up superpositions like this, if it occurs as an error, I'm saying. So from an error analysis point of view, these are very bad operators to actually happen. But as controlled operations that we perform, they are the logical X and the logical Z operations. They are the X and Z gates that we will perform on the encoded qubits when we start putting together these encoded qubits and start doing quantum computing with them. right? So X bar and Z bar also serve this purpose of representing at least a pair of the Pauli gate set, at least some of the gates that we need in order to do universal quantum computing. Okay, fine. So I would also like to, so I'll discuss gates, logical gates a bit more. That's the next thing, in fact, that I want to discuss, but I also want to write down two other stabilizer codes at least. So there is a larger theory of stabilizer codes which connects back to classical codes, okay, classical linear codes. It connects back to something called CSS codes. This is not something that I will have time to discuss in this course because it will occupy another week, and I really want to get to also Shannon theory at least next week. So let me just mention these two other codes, and then some of you, if you are interested, you can actually read that up as part of your term paper or presentation. Okay, so the third code I want to write down is actually the 513 code. So if you recall, we discussed the quantum Hamming bound. Where we said that the shortest code that you can have is basically a 5-qubit code, right? The shortest code that you can have to correct for a single qubit error right, is a 5-qubit code. So what is this 5-qubit code? So pretty early on, such a code was identified. So it turns out that when the code was identified, it was not really identified as a stabilizer code, okay? Because the whole stabilizer construction came much later. Shor's code was one of the earliest to be identified. The 3-qubit repetition code, of course, was also identified. But a code that saturates the quantum Hamming bound, right? Because it was a bound, right? It said that the smallest n you can have, if you want k to be 1, is basically 5, right? So is there such a code which can saturate the quantum Hamming bound? And it turned out that there was indeed such a code. So let me write down the code words. So remember, the code words are now in a 5-qubit space, right? So you will see how messy it is to actually write down these code words. So they are actually massive superpositions of all these 5-bit strings. How many 5-bit strings do you have? How many basis states, computational basis states will you have for this 5-qubit space?
2.
Exactly.
2.
So you will see through the 5, yeah. So each, the 0 logical will be a superposition of 16 such 5-qubit states, and the 1 logical will be a superposition of another 16 such 5-qubit states. So you'll have a 1/4 overall, and then you have, so you see that there is a parity angle to this. All the states that I'm writing down will have an even number of ones. See, I missed a minus sign. So as you can see, obviously I'm copying this from somewhere. There's no way that I'm writing this from memory. But anyway, so maybe I'll refer you to Nielsen Schwank for you to see this full state. But it's basically a superposition of 16 out of the 32 computational basis states. So this was worked out in a very brute force manner, actually. So people wrote down all possible, all of these 32, 5-bit strings, and then they put various phase factors, and then they asked what kind of combinations can satisfy the error correction conditions. And you know the form of the error correction conditions which you wrote down for your mid-sem, where you wrote down the error correction condition not in terms of the projector, but actually in terms of the code word itself. If you write that down for all the single qubit Pauli errors, then you will get constraints on all these relative phases. Okay, so they showed that first of all, it is sufficient for these phases to be plus minus 1, and then they obtained a constraint on all these relative phases, and then they identified these code words, and there was some symmetry in this. Like I said, these are all even parity, and the other one will have all odd parity states. So this will have the 5-1 state. Then it has the 3-1 states. Right. And then it starts having the single 1 states. Etc. etc. Okay. So again, this has another 16 computation basis states, and this is what describes the code space. So the code space will be, so the 5-qubit code space is the span of this 0L and 1L. Now it turns out that there is a beautiful description of this code simply in terms of a stabilizer group. So of course, once you have the code words, you can go back and ask, what is this? Is there, there has to be, as we discussed already, there has to be a stabilizer group that's associated with it. So what is this stabilizer group? It turns out that, so how many generators should this group have? You're encoding 1 qubit in 5. So how many generators should this group have? NSEM exam question.
4.
Minus k, n minus k, 4.
Exactly. Yeah, 4. Good. So these are the 4 generators, and they again have a nice permutation symmetry. So if you notice, these states themselves will have a permutation symmetry among them, right? Because all these strings, you will see there is some permutation symmetry happening here. So this is basically like this. So it's I, X, Z, Z, X, then X, I, X, Z, Z. So now if I write down 1, I can actually write down all of them. So then the last one will be the Z. I'm writing down the independent operators alone. So it will be Z, X, I, X, Z, right? So these are the 4 stabilizer generators. Oops. And now, based on the fact that, say, the 0L has only an even number of 1s all the time, can you identify what the logical Z operator will be? That's the one which leaves it invariant, right? Will it be the all? So the obvious things to try are the all Z and the all X, right? So will it be the all Z or the all X? So what will the all X do? That should become clear, right? So what does X1 to X5 acting on 0L do? Sorry?
Ma'am, all Z can be.
Yeah, so the logical Z will indeed be the all Z operator actually. Yeah, sorry, I didn't put the 1, 2, 3, 4, 5. I hope you see that. And because, well, you have an even number of 1s, right? So this is going to leave all the signs invariant. It's going to leave the state itself invariant, right? But if I do the all X, you will see that it actually flips, right? Because it takes, it changes the parity of all the bit strings, right? It takes the all 0 string to the all 1 string, etc., etc. So actually the all X will be the logical X and the all Z will be the logical Z, right? So notice that what this also means, like I said, is it gives you a way of physically implementing a Z gate on the encoded qubits. So now it's easier to draw. I have 5 encoded qubits, okay? So I have to do basically an operation like this: Z, 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 Z. And if I do this operation on the 5 qubits, this is equivalent to drawing this in the circuit. I have an encoded Z operation or a logical Z operation on the encoded qubits. In the case of the Shor code, this is exactly flipped around. So I'll have to do a series of X's to realize this kind of a encoded Z operation. Okay. Finally, I also want to mention the 7-qubit code. So while the 5-qubit code is nice, and it is indeed the shortest code that can correct for arbitrary single qubit errors, it turns out that from a different perspective, the 5-qubit code is not nice. Okay, and what that perspective is, we'll get to tomorrow when I talk about fault tolerance. Okay, it turns out that from that fault tolerance perspective, the 7-qubit code is actually nicer. Okay, so I also want to write down the 7-qubit code. So this 5-qubit code actually, to the best of my knowledge, does not really have a classical analog. Okay, it's a uniquely quantum code because it saturates the quantum Hamming bound. The 7-qubit code, on the other hand, was inspired by a classical code. So let me write down the last one. So the 7-qubit code is also often called the Steen code. It's associated with one of the giants of classical error correction, Steen, whose name also appears in CSS. CSS is Calderbank Shore Steen codes. Okay. So the 7-qubit code, again, I don't want to spend time writing down the code words, but let me just write down at least the stabilizer generators, if I can find it. So this is a 713 code. Okay, and this actually comes from what is called a classical CSS code. Okay, and just give me a second. So once again, you're just encoding a single qubit in 7 qubits. So these code words again are massive superpositions of the 7-bit strings, but thankfully not all. I mean, now you have like 2 to the 7 of them, right? So they don't involve, like the 5-qubit code, they don't involve all possible strings. Yeah, I can just write down the stabilizers maybe, but I think it'll be useful to give a glimpse of the 7-qubit code words. Yeah, here you go. So there's only 8 of them that are used in the superposition. So there is the all 0. So there is a way to go from the classical code words to the quantum code words when you make quantum codes using classical codes. Okay, so this is, in the classical setting, this is called a 743 Hamming code. Okay, so the classical code that it is coming from, let me just write that here, is what's called the Hamming code. It's a well-known classical code. So of course, the classical code will have certain code words, right? Binary strings. So it's easy to then make the quantum code words from that. There is a way to do it. I'm not getting into that right now, but I just thought I'll give you a glimpse of this thing. So there's a set of 8 states, like I said. Again, there is a parity angle here that you will have, all of them will have 4. So you see the 743 will actually tell you that there are 4 1s and 3 zeros. Okay, as far as the 0 logical is concerned. The 1 logical, of course, apart from the all 0 state, and then you have the all 1 state in this, right? So if this is 0 logical, naturally the 1 logical must have, you know, the all 1 state out here. And then you again have, in this case, the parity is exactly flipped. So you will have 4 zeros and 3 1s, which is the opposite of what is there in that. Okay, what is there in the 0 logical. All right, so another set of 8 computational basis states. So once again, it's nicer to write this in terms of the set of operators that stabilize these states rather than the states themselves. It is bulky to write the states. So there are, again, how many stabilizer generators should I have? So it's a 7-qubit code that corrects for a single qubit error, all possible single qubit errors. How many generators should I have?
6.
Yeah, indeed. Good. So I should have 6 generators. So this is 2, 3, 4, 5, 6, 7. Once again, you see the 4 coming in here, right? You should see this from the structure of the code words also. So there will be 4 X's like this. I'll drop the, okay. So this has 1, 3, 5, 7. So there are 3 X stabilizers and 3 Z stabilizers here. So these are the 3 X stabilizers. So let me write down the Z stabilizers here. Once again, the Z exactly mirroring the X attributes. Five, 6, 7. Okay, so these are the set of 6 operators that stabilize them. And once again, you can identify what the logical Z and the logical X are. I will let you do that. Okay. So again, with the even parity, I hope it's clear that the all Z operator will be the logical Z. And the all X operator will be the logical X. Okay. Did I write 7 of them? All right. So there you go. That's the 7-qubit code with the 6 stabilizer generators and the logical X and Z operators. Okay. So yeah, like I said, each of these codes had their origins in different places, but they all fit together nicely under this umbrella of the stabilizer codes, right? The Shor code was inspired by the repetition codes, concatenating 2 repetition codes. The 5-qubit code came by a brute force calculation of, what are all the 5-bit strings which you can put together to form a code that saturates the Hamming bound, which can also satisfy all the error correction conditions. And finally, the 7-qubit code actually came from a very important classical code called the classical Hamming code. And all of them are quantum stabilizer codes. Okay, fine. So the next thing, like I said, is to talk about so we can talk about a couple of things, right? First of all, implementing the stabilizer code. So maybe I should just complete today's lecture with that and talk about the logical gates part tomorrow. So I have another 10 more minutes maybe. So just a word about implementing the stabilizer codes. So as far as implementation is concerned, you have preparation. So what are the different steps that I go into implementing an error correcting code? Remember, we started drawing these circuits very early on for the 3-qubit code, even for the Shor code. So what I call preparation is basically what we earlier used to call the encoding circuit. Right? So we need an encoding circuit, right? And then we need, and then of course, let's say the noise acts on it, right? And then we have to talk about the decoding, right? So what we need to implement are the encoding and decoding, which means here you need to talk about syndrome measurements, right? So there is the encoding aspect and then there is the decoding aspect. And the encoding as well as the decoding can all be described purely in terms of the stabilizer generators, right? So how do you describe the encoding in terms of the stabilizer generators? In terms of the logical operator, right? So what does the logical operator tell you? It tells you that you need to identify. So once I've identified the stabilizer group, once I've identified the Z bar, then the preparation circuit, so to speak, which is the encoding circuit, is basically something which has to project onto the +1 eigenspace of this whole thing, right? The stabilizer generators, comma, the Z bar, right? If it's a single qubit code, for example, right? So just by doing this measurement, right? So in particular, so let me just write this out. So how will I do this implementation? So I start with, so let me say 1 and 2. So start with suppose you start with the all zero state in the n qubit space, right? So that's how you'll typically start, right? Remember that even with the 9 qubit code, you started with all zeros and then you started putting Hadamard's, etc., C naughts, and that's how you got the encoding circuit. So you start with your 0 tensor n, okay? And then all you need to do, so one way of doing this, right, rather than thinking in terms of an encoding circuit, is you need to start measuring. What do you need to measure? Measure each generator of the stabilizer group, right? Every measurement will either give you a +1 or a -1. And with each +1, remember these are a set of commuting operators. With each +1, you measure the next generator, right? So you do this basically a simultaneous measurement of a bunch of stabilizer generators, followed by finally a measurement of Z bar, right? And once you have projected down to the +1 outcome in all of these cases, what will remain is the zero logical. So it's basically a sequence of measurements of G1, G2, etc., Gn minus k, and then, well, the Z1 bar, the Z2 bar, how many ever logical qubits there are. So if I said k, then there's going to be Z2 bar, etc., Zk bar, right? Such that, so where the outcome +1 is selected each time. What I mean by that is if the outcome is -1, then you have to go back, right? Or you have to keep track. So if the outcome was -1, then you simply have to keep track of all the -1s. And then the state that you will have is not 0L, but it will be one of the other logical states, right? So either you think of it as post-selecting all the +1 outcomes, or you keep track of the plus and minus with every measurement. And then the final state, after you have done this entire sequence of measurements, will basically be that logical state, which has ones wherever there were minus outcomes, right? So you just keep track of all the measurement outcomes. And if you post-select, so this is what is called post-selection, typically, then you can basically project onto the logical 0. And once you have the logical 0, then you can get all the other code words via some other logical operations, right? Similarly, the decoding, now decoding, remember, is typically two parts. There is the error detection and the error correction. So let me write this actually as error detection and error correction. So the error detection happens, we've already seen this with several examples, happens by measuring the stabilizer generators. So if I have a noisy encoded state, that's the incoming state now, right? I again put a bar to denote that it's an encoded state. I now have to measure all the stabilizer generators, G1, G2, etc., Gn minus k. And whenever I get a minus outcome here, I know that an error has occurred, right? And corresponding to whichever generator it was, I know what error has occurred, right? So based on, so again, I have to keep track of the plus and -1 outcomes. right? So I basically have binary strings of length n minus k, right? So remember that we had already done this again for both the Shore code and the 3-qubit code. So the 3-qubit bit flip code, you have these two generators, right? And you had a binary string of length 2. Based on which binary string of length 2 you had, you could go back and identify which of the set of single qubit errors occurred. And depending on that, you simply had to do a single qubit X or a single qubit Z as the recovery operation. And based on this, you do the recovery operation. Right? So this is how you will do the error detection and the error correction completely in the stabilizer formalism. So the reason I'm saying all this is to give you an idea that recasting everything in terms of stabilizers and logical operators provides an efficient description for the entire error correction process. You no longer have to keep track of individual states, right? You simply can keep track of these operators, and you keep track of classical syndromes. So these are the classical syndromes, right? This set of plus minus ones, and based on which of these occurred, you know which error occurred, where the error occurred, right? And based on that, you can do the error correction, right? So instead of having to keep track of states, so let me just make this final remark here. So all of this we've done examples of, so I'm just abstracting out this in a very general sense. So the idea is that instead of keeping track of states which are exponential in n, we keep track of the stabilizer generators. And how many generators are there? N minus k. So that's linear in n, right? So describing the entire computation or describing the entire error correction procedure in terms of the stabilizer generators helps you to keep track of this entire process. It becomes something which is linear in the number of encoded qubits as opposed to exponential. What that then gives you is that it makes this whole process efficiently simulatable on a classical computer. So at the very least, now you know that your syndromes are something that are linear in n, right? Well, it scales as 2 to the, I mean, there are n minus k binaries, binary strings of length n minus k. No doubt that has an exponential in it, but it's not, for example, something that is double exponential in n. Whereas if I were to keep track of states and ask what happened to each individual state, then you're going to be keeping track of something which is 2 to the n over and above the classical syndromes. But now you're only keeping track of something which is linear in n, right? Which means that this entire process becomes efficiently simulatable on a classical computer. But this is not the last word, because I have not told you yet anything about gates, right? I've told you about the encoding or the preparation, which involves, again, a linear set of measurements, a linear number of measurements, again, keeping track of plus minus 1 outcomes at each stage, right? And the decoding process, again, is a number of measurements which is linear in n, and once again keeping track of plus minus 1 outcomes there, right? However, what comes between, right, or what comes, what we've not yet discussed is how to do a complete computation, right, purely in terms of these logical operators. So what are, how does one talk about logical gates? And when can you now sort of draw the boundary between when something becomes classically simulatable and when it is not? Okay, so we'll discuss this tomorrow. It turns out that this leads to a very nice theorem called the Gottesman theorem, which tells us when a quantum computation is efficiently simulatable on a classical computer. Okay, so let me stop here. Any questions?
Ma'am, just a few slides back, you introduced the 5, 7, and 9 qubit codes. So I
Yeah.
wanted to know that is there any specific reason why we don't have the 6 and the 8 or anything other than those three?
Yeah, that's a good question. So 5, because it was the shortest, right? You know that there can be nothing shorter than 5. There is a 6 qubit code. There is what is called a 622 error correcting code. Okay. So the 6 qubit code that we know, it turns out can actually encode 2 qubits. Okay. But has lower distance. So when I say 622, so there is indeed a 622 code. Okay. So it encodes 2 qubits in 6, but it can detect single qubit errors, cannot correct any single qubit errors. So this kind of a code actually works well as what is called an erasure code. Okay, because it can detect errors. Remember, d-1 errors it can detect. So this 2 minus 1 is 1. So it can basically detect for single qubit erasures, right? And if you think of your noise as only erasure, then it is an erasure correcting code. Okay, but it cannot correct arbitrary single qubit errors, right? So yeah, so we don't really have a 613 code as far as I know. Okay, not for qubits. It's possible that if you go for higher dimensional alphabets, like if you go for qubits, there are more possibilities. Okay, but as far as qubits are concerned, what we have is only a 622 code. Now, why don't we have such a code? Basically, we'll go back to the constraints that one puts in as far as the having to have a certain number of stabilizer generators which satisfy certain conditions, right? So if I need a 613 code, I will have to have 5 stabilizer generators, all of which satisfy the error correction conditions, right? And as far as we know, such a set does not exist. And 6 is a kind of funny number as far as quantum information is concerned in general. So I don't have a good answer for why we don't have a arbitrary error correcting code of 6 qubits. The 7 qubit code, by the way, is also a code that saturates a different bound called the quantum singleton bound. Okay, so the Hamming bound was one way to get a bound on the size of a quantum code. There are other ways. There's something called the Gilbert-Varshamov bound, and there's something called the singleton bound. So the 7 qubit code saturates one of these bounds. So that's why that code is also special. The 7 actually comes from taking 2 classical codes and putting them together. So for 6, again, there are no pairs of classical codes which can be put together to form a 6 qubit code. Okay. So the 7 basically comes from combining a 4 and 3 kind of classical code. Yeah, so this is the best answer that I have at this point. Okay. Yeah.
And ma'am, one more thing, like when you were talking about how should we use the stabilizer formalism, you said that we need to perform measurements on the array of the qubits for each of these stabilizer generators. I mean, I wanted to know that once we have performed a measurement, doesn't that destroy or collapses the the state of the system? So wouldn't I mean, how should I proceed after the first measurement in that procedure?
Yeah, so this we've sort of discussed, right? So what do? We then attach ancillas, no? We don't directly measure the encoded qubits. We will attach ancillas, right? And what we will do is to perform some joint operation here, which is typically like a C0, and then we will measure here, right? Whereas these are not disturbed, right? If you remember, as far as the 3 qubit code was concerned, This is how we measured we were effectively measuring we were doing two Z measurements on the ancillas, if you remember, right? And that was effectively like measuring Z1, Z2 and Z2, Z3 on the encoded qubits, because you were doing C naughts accordingly. You were doing a bunch of C naughts. So that effectively this turned out to be a measurement of the stabilizer generators on the encoded qubits, but you were not really touching the encoded qubits. So that's how you will always do the
Then
measurement.
using the doesn't using the ancillas destroys the whole point? I mean, we are then using a more number of physical qubits than what should have been used in the stabilizer procedure, right?
Absolutely, absolutely. So this is something which is brushed under the carpet, right? So when I say that my code has only 5 qubits, indeed, you have to then ask. So this is why I said the 7-qubit code is a nicer code than the 5-qubit code, precisely for this kind of a reason. The number of ancillas that you need to stack up and the number of C naughts you need to do, all of that goes into the physical resources that you need to doing an error correcting code. Right? Because indeed, there's no way, if you keep measuring the data qubits, you'll have no quantum computing, right? You have to keep extracting syndrome out and keep measuring ancillas. And only then can you leave the encoded qubits free to perform some computation on them. So when I talk about whether something is a nice error correcting code, it's not just about whether it saturates a particular coding theory bound. You have to ask, what about its implementation? Is it something which is amenable to a nice implementation? So tomorrow I will talk a little bit about this, where I will talk about even doing the encoded operations actually becomes much harder for the 5-qubit code, becomes much nicer for the 7-qubit code. Even these ancillas, it turns out, you can keep reusing them. So although these ancillas are a resource that gets consumed, once I extract one syndrome, so once I get one pair of syndrome bits S1, S2, I can initialize these ancilla qubits again to 0, and I can again, do another bunch of C naught. I mean, I can kind of reuse them, right? So indeed, it turns out, for example, that to do a 7-qubit code, to implement a 7-qubit quantum error correcting code, I need at least 49 qubits. Okay, I will need, those are all that, includes all the additional ancilla qubits that I need in order to not just implement the 7-qubit code. So if I just want to implement the 7-qubit code, it's only 14 qubits that I need actually. But if I want to do it, what I'm going to talk about tomorrow, fault tolerantly, then actually I need 49 qubits in order to just implement the 7-qubit error correcting code. Okay, yeah, so we'll discuss some of this tomorrow. So I want to talk a little bit about this implementation aspects and fault tolerance tomorrow. So yeah, I'll get to this tomorrow.
At least for the generation of qubits, we'll have to start off with multiple n-qubit zero states, right? Only then we'll get few logical zero.
Yes, if you do this post-selection procedure, which I mentioned here, indeed, you have to, because there's only a certain probability that if I do a sequence of measurements, I will project onto the zero logical. So I'll have to repeat this preparation circuit many, many times. It turns out that repeating the preparation circuit many times is desirable even from a fault tolerance point of view, right? Because what is fault tolerance? Basically, these individual measurements can be faulty, right? So far, I've said everything, I've assumed that everything except the qubits are perfect. It's as if only the qubits get affected by noise and all other things that I do to them are all like picture perfect. That's not the case. So now, anyway, it's useful to actually repeat this kind of a preparation circuit. This is a probabilistic preparation procedure. So it's good to repeat this a few times in order to make it fault tolerant. So the kind of big encoding circuit that I drew for the Shore code is not something that may actually be physically implemented, because that will have tremendous number of faults when you try to implement something like that. That's actually a pretty unwieldy encoding circuit to implement. So this kind of a stabilizer measurement and some sequence of measurements actually turns out to be a nicer way to do the preparation. It is probabilistic, but it's always anyway good to repeat this procedure a few times. So yeah, all of this goes into, the kind of resources that you need in order to implement error correction.
When I had a small doubt from the previous lecture, we had defined D as the minimum number of minimum weight for which it will commute with all the states in S. But then
All the
how do we
generators
know?
of the stabilizer.
Yes,
Yeah.
yes, all the generators of the stabilizer. So how do we know any weight greater than this will also commute? Because that's how we assume that d minus 1 till d minus 1 we can correct.
Yeah, but that tells me that at D I cannot correct. It's possible
Correct.
that there may be some D plus 1 that I can
Okay.
still correct. But
Okay.
at D that breaks off, right?
Yeah, because in source code there were few which were greater than d which were correctable.
Correct, indeed. Yeah, yeah. If I pick the X locations appropriately, yes, I will still be able to correct some 6-qubit X error probably, right?
Okay.
But yeah, or maybe an odd number, so maybe a 5-qubit X error or something. Yeah, but no, when I want to know the capacity of a code, or when I want to know the performance of a code, I want to know up to how many errors can it truly tolerate and correct for. Anything else is bonus, right? And those are stray things which I cannot fit into this. But if I say up to this many errors I can always correct, then that's a guarantee, right? That's what the distance tells you.
Okay, thank you.
Yeah, sure. Okay, so we've actually gone on for much longer today. So I'll see you all tomorrow.